Hey guys, so once again welcome back to Chilifili, and in this video we're going to see what is the difference between linear regression and polynomial regression and when we should use polynomial regression. Okay, so in my last video I talked about how we can implement simple linear regression and multivariable linear regression using normal equation, and in this video we are also going to use normal equation to perform polynomial regression. Okay, so in simple linear regression, what we used to do was to find a straight line with a slope and an intercept that best fits our data. But there was a problem that we were getting less accuracy for our model, and our ultimate goal is always to build a model with the maximum accuracy and minimum errors. So in this video, we will see how we can implement polynomial regression that best fits our data by using curves. So here is a simple example, and the blue dot represent our data set, and this is a simple linear model, and we have implemented a best fit line that goes to our data set, and as you can see the error here is way more than the error in this polynomial model. So polynomial model just plot a curve instead of a straight line. Okay, so before going there, here are some basic polynomial functions with its graphs plotted, and this will help you understand better on which polynomial to use for a specific data set. Okay, so the first graph is for y equals to x, and as you can see it's a straight line with a slope and an intercept value. Okay, so the next graph is y equals to x square, that is shaped like the alphabet V, and the next graph is for y equals to x cube, and this look like this. Okay, so now here is the important part. See, here I have implemented the graph of y equals to x cube plus x square plus x, and the graph for y equals to x cube. The blue dot is the graph of y equals to x cube, and the red dot represents the graph for y equals to x square. Sorry, y equals to x cube. Okay, so here you can clearly see that the biggest power influences the shape of our graph. See here, our red dot represents this graph y equals to x cube plus x square plus x, but here the highest power is 3, so the graph of our equation for y equals to x cube plus x square plus x is going to be like the graph of y equals to x cube, that is right here, not like a graph of x square or the graph of x. Okay, so that is the point to be noted here. Okay, you can clearly see that the biggest power influences the shape of our graph. Okay, so now we are going to see why we should use polynomial regression, and here I am going to take an example, and then for the first section I will find the linear regression line and calculate the error for that, and for second section I will use polynomial regression and find the curve that best fits it and calculate the error. After then we will compare both of this error and see which model performed better. Okay, so here I'm going to take polynomial function for generating dataset, as this is an example where I'm going to show you when to use polynomial regression, and I'm going to add some noise so that it looks more realistic, and we are going to use the same normal equation which we used to implement for simple linear regression. So if you haven't watched my previous video on simple linear regression using normal equation, then I think you should watch it first. Okay, so moving forward, this is our normal equation that we are going to use, where theta is the hypothesis parameter, or the parameters that are optimal that we want to find for our graph, and x is the input feature and y is the output feature. Okay, so first we are going to see the simple linear regression here. So the hypothesis function for simple linear regression is the beta 0 plus beta 1 into x, or you can say beta 0 is the y-intercept here and beta 1 is the slope of the line. As it is a simple linear regression, our hypothesis function is the equation of line. Okay, so let's move here to our Jupyter notebook where we can actually implement it. Okay, so let's start it. First of all, we need to import some required libraries, that is NumPy and Matplotlib. Here matplotlib is for visualization and numpy is for calculations. Okay. Okay, after then we are generating some data points. Here I'm going to use the arange function, and the parameters for arange are start point, end point, and the step size. So it is going from -5 to +5 with the step size of 0.1. So it is going to be like -5, then -4.99, and so on. Okay, so as this is the example of polynomial regression, we are going to use or we are going to generate the polynomial data set for it. So it is nothing but x cubed plus x squared plus x plus 1. Okay, so what if we just plot only this data, or what if we don't add the noise for our data? So let's see what happens. I'm going to copy this, and let me just grab a new tab here, and sorry, I'm going to do it on scatter plot, so x and y. Okay, here you can see I have not added any kind of noise, and the graph is like the graph for x cube, right? And our realistic data does not look like this. Okay, so what we are going to do is we are going to add some noise to it so it looks more realistic. Let me execute it. Okay, here you can see it looks a bit more realistic than this. Okay, so how we can add noise? So we can add noise by np.random.normal, and this generates random values that follows the normal, what do you say, that the bell curve, and normal distribution, and the size for it is going to be the length of x or length of y, both of are same. Okay, so after then I'm going to add the y noise that we just calculated to our y data points, and just we are going to scatter it. Okay, after that what I'm going to do is find the shape of x, that is 100. So we have 100 rows, and okay, here is the important part. What I'm going to do is build our matrix x. So if you haven't watched my previous video, or if you haven't read my previous articles, then you might not know what are we going to do here. So first of all, I think you should probably watch my previous videos to understand better. See, what our matrix x is, it takes the first column as 1 always, because that is the coefficient of our beta 0. So as you can see, the coefficient of beta 0 is going to be always 1, and after then we are going to take the x value here in the second column of our x matrix, and then here is the value of our y vector. Okay, and here are the parameters that we want to find. Okay, so what are we going to do is generate this one column. Okay, and after then we are going to append it with this x vector and multiply it with our optimal parameter values that we want to find, and we are going to assign it to the y vector. Okay, so let's do it step by step. Okay, first here I'm going to calculate the length of x, so that we know the number of rows that goes in this x bias. Okay, so it runs fine, and then I'm going to find the shape of x bias, so that is 100,1, and the shape of x was 100. So to add or append our data to another vector, we need to make sure that they both have the same size. So I'm going to reshape my x to the shape of x bias. Okay, so now what I'm going to do is append our x vector to this x bias that was just 1, as you can see here. Okay, so I'm going to append it. It works fine. Okay, now why am I going to find the transpose? Okay, so if you know the equation of normal equation, then you might notice that we want to find the value of x transpose dot x and its inverse. So first of all we need to find the value of x transpose, then we are going to multiply it with the value of x, and then we are going to find the inverse of it, and after that we are going to multiply it, or we are going to find the dot product of x transpose and y. Okay, so we are going to do it step by step. First of all, I'm going to find the transpose. Okay, that works fine. Then I'm going to multiply it with the value of x. Okay, so here we go. And after that I'm going to find the inverse, and I'm going to store it in a variable called temp1, so that after that we can multiply. Let's say this is temp1 and this is temp2, so we can finally multiply those two. Okay, so here is temp1 and here is temp2. That is the product of x transpose and y. As you can see here, that is the product of x transpose dot y. Okay, so now what we have is our coefficient values, that is the dot product of temp1 and temp2. Okay, so now we already have our uh, optimal parameters. So what we can do is plot our regression line. So first of all, I'm going to plot the actual data set, and then I'm going to use our equation of line, that is y equals to mx plus b, or y equals to b plus mx, where m is the slope of the line and y is the y-intercept. Sorry, b is the y-intercept. So here I'm going to take the first parameter, or the first first element of an array, to as assigned as a b, because that's what we took here. Like as you can see, the first one was beta 0, so we assigned it a coefficient of 1. Okay, so let me just plot it. Okay, as you can see here, okay, just let me assign different color equals to red. Okay, so now we can see that if we don't know about polynomial regression, then this is the line, or this is a straight line that best fits our data. Okay, so now we can see that for each of this point there is some kind of error here, and let me calculate it. And I've already made a video about how we can calculate such errors in our regression, and I will put the link in the description if you want to know in detail. So it is nothing but we are going to just predict the value first, and we are going to compare it with our actual value. Okay, so this is the prediction function here, and then I'm going to predict it with our optimal parameters, and this is the definition or function for calculating the mean squared error. Calculate mean squared error. Okay, so it just subtract the original value from our predicted value, and then we are going to multiply it, so it is going to be squared, and then we are going to take the mean of it. Okay, so let's see what is the error here. Oh, it's a lot bigger than I thought. It is around 5 million. Okay, so now what we need to do is to find a model, or find a curve that best fits our data. As you can see here that our straight line is not working very well, as it is given us a very high rate of error. So let's move forward to our second part, our second section, and in this we are going to do the same procedure as we do in our first section. Okay, so let's get started. So first of all, I'm going to import some libraries and generating the data. That was same procedure, that is the same procedure as we did in our first section. Okay, as you can see here, traces our data. Okay, so now what we want to do is we want our function. Okay, just let me get back here for a second. We have done all of this, and now we are going to, okay, so this is the hypothesis function for our polynomial regression, that is beta 0 plus beta 1 x plus beta 2 x squared, and up to beta n and x raised to n minus 1. So here are the parameters or coefficients that we need to find to find the curve that best fits our data set. Okay, and here you can see that x square and x cube are the features of our data set. In our first section, what was the feature of our data set? That was only x, right? We only took into account x only. So here we had only one column here. But now what we have is we have more than one parameters or more than one elements in our regression hypothesis function. So we are going to add more columns here, for one for x square and one for x cube. We already have this in our simple linear regression, so we are going to add a column for x square and x cube. And as you can see here, this will be our final x matrix. Okay, so let's go ahead. So here you can see the x1 is x and x2 is the squared value of x1 and x3 is the squared value of x1. Sorry, x3 is the cubed value of x1. Okay, so let me just print type of a. It's already array, because while we are working with the matrices, then we must keep in mind that we already have our data in array. Then I'm going to just find the length of a so we can append it. Okay, so now what we need to do is reshape our data, because our x bias is going to be 100,1 and this is already 100. Okay, let me just print it. It's 100. So I'm going to reshape it. Okay, and this is our first vector that we find here. This is the first vector, one vector. Then this is the x vector. After then we will have x square, and after then we will have x cube. So we are going to append it one by one. Okay, so first of all I'm going to append the x1 vector to our x bias vector, and then this new vector with x2, and after then this new vector to x3. Okay, this is pretty easy to understand, and if you need to know more about this, then I've already made a video about it and I already wrote an article about it, and you can visit my blog, or I will put the link in the description if you want to read it or if you want to watch my previous videos. Okay, so let's see how our data looks. Okay, see, here is our first column, that is all one, and here is our second column with our x values. This is our x square value and this is our x cubed values. See, the next procedure is same as the first section. So first we are going to find the transpose of it, and after then we are going to find the dot product of the transpose value and our original value, and after then we are going to inverse it, and after then we are going to find the transposed value for x and multiply it with y. Okay, as you can see here, this is what we are doing right now. Okay, and this will give us our optimal parameters. So you can see it returns an array. So these are our four parameters. So this is beta 0, beta 1, beta 2, and this is beta 3. So beta 3 is the coefficient for x cube, this is for x square, this is for x, and this is just beta 0. Okay, so let me run it. Okay, so now we want to plot a graph that has equation like let me just grab a pen here. Okay, so we want our equation to be like okay, let me just get it here. Okay, here it is. No, okay, okay, here we go. So first of all we have a beta 0. So I don't think it is working. I should just probably show you in the article. Okay, so let's see. What we need to find was beta 0, beta 1, beta 2, and beta 3. Now we already have it. We need to our we need to find our regression line in this form, that is beta 0 plus beta 1 x plus beta 2 x squared plus beta 3 into x cube. Okay, so why are we stopping at x cube, since we already know that our graph or let me just show you. Where was it? Okay, here it is. That our graph looks like this. So we are going to stop at this, and if our graph looked like the shape of alphabet V, then we might want to stop at x square. Okay, so let me just plot it. Okay, here you can see that it is better than our graph here that was just going straight through our data points. Okay, so let me quickly find the error. So it is like same we did here in the first section. I'm also going to use the mean squared error, and let's see what's the error. Yes, as you can see, it is only 338 and it's only three digits, and the error here was in 6 digits. Okay, so as you can see, using polynomial regression is more beneficial when you have curvy data or when you don't have linear data. Okay, so I think you guys got it, and let me just get back here so that we don't forget anything important. We covered this, and this. This is pretty easy to understand. We already defined the error function, calculated. Okay, so here you can see the error is significantly lower than the error in linear regression. So we can say that it has done pretty good work. So in conclusion, we can say that if dataset is following curve trends, then we can use polynomial regression for better results and accuracy. Okay, so I think that's it for this video, and if you guys like this, then please hit the like, share and subscribe button, and in the next video we will see what is exponential regression and how we can implement it using Python. So okay, thank you so much for watching, and I will see you guys in the next video.